Hello. Yeah.
Yeah, okay. So our next speaker is Baz. We'll be talking about related description and complexity for our parameters.
Thank you, Bomedine. And this was like very interesting talk since the morning. And I'll try to add um, more discussion to the same topics. And today we'll be talking about minimum description length. And we try to revisit these notions for overparameterized models. This is joint work with my PhD advisors, Binyu and Martin Wainwright, another PhD student who is now graduating, Chandan Singh. And currently I'm doing a postdoc, so that's why the affiliations look different. So this was work done during my PhD. So the motivation of the work comes from the things that I think are talked about, this double descent phenomenon. And so the classical wisdom in bias variance trade-off, is that you should pick a model. I pick the simplest model that fits the data, and the typical curves look like there is some complexity on the x-axis. And as you increase the complexity, bias goes down, variance goes up, and there is some sweet spot that you should pick. But the modern phenomenon, starting with called double descent, but now they call it fit without fear, is that you just keep picking the largest model that interpolates. And the reason is that we see this U shape, and then after some time, the risk starts to go down. And somehow, as you go down further and further, you can still win. So so that's like the double descent or non-U-shaped risk curves. And the starting point of this work was, is there can we move that thing? Okay, maybe now. So is there a conundrum compared to classical wisdom, this double descent phenomenon, or can we actually see it in some modified version using the wisdom itself? So one thing to note is the classical U-shaped trade-off assumes that you have a fixed data set and you're varying the complexity of the fitted estimator. And we were trying to tackle with a lot of theoretical literature which tried to characterize this double descent. So often they would change the data set as they moved on the x-axis. So this is just trying to say that let's fix the data and change the complexity of the estimator. But even for like just simple estimator, like if there was a zero estimator and I fix the data set, you know that the risk will be flat. There's no descent, there is no trade-off. And this min norm OLS shows this kind of, double descent, because the variance, it goes down, then goes up, and then goes down again, and goes up again. And if you do slightly more, weird things, you can have multiple descent. So you can have you can create all kinds of patterns just by changing the design and playing with the estimator. So I think one thing to note is this U-shaped trade-off, we believe you should restrict attention to a good estimator class. So even though we had these fancy descents, if you consider a tuned ridge estimator in these simple problems, you still see the U shape. So that's one thing to note, that double descent is often because of the instability of the estimator in certain regimes. So it's about, for OLS, it's around when the number of parameters is the same as the number of samples. In like weird OLSs, it can happen for other reasons. And there is all kinds of regularization that is going on that stabilizes it when you're away from these unstable regimes. But the point is, if you want to understand this double descent from in the classical bias variance trade-off sense, then we should pay attention to the estimator class as well as the complexity. So that's the other thing that governs this trade-off, like what is on the x-axis. And there were a bunch of talks like previously in this session that tried to change the x-axis, but the typical curves that are shown in literature assume the number of parameters as the x-axis or the width of the network as the x-axis. And that motivated one of the works that started this work so we know that we need to pay attention to the estimator class, but have we settled on what the complexity should be? Like, it's very fitting to this seminar. And should we really use parameter counting? Of course, this audience will easily believe, no, we should not be using it. And you were trying to say, like, can we derive some other notions starting from first principles? So D is the number of features or like covariates, and N is the number of samples. So complexity, I mean, it's a tricky concept in some sense. Of course, in this symposium, it has been a lot of discussion about Kolmogov's algorithmic complexity. And one of the typical criticism is not computable. In statistics and machine learning, the way people use complexity is basically they want to write test error bounded by training error plus some notion of complexity by sample size. And that's what our point was like in this bias variance trade-off curves, the x-axis is usually not well defined, often vaguely defined, and typically literature uses parameter count. So one might ask, why do we use parameter count? And there are a bunch of good reasons why people use it. Is because a lot of classical notions of complexity simplify to D, like the parameter count itself. For example, a Kaike information criterion in 70s, then Bayesian information criterion, D is the number of parameters, Rademacher complexity, degrees of freedom, VC dimension, and even minimum description length, which is what this talk is about. They all simplify to order D in D dimension. And the other reason why people like this complexity measure is because we know that like good estimator, OLS is a good estimator in low dimension. It achieves this minimax risk of order D over N. So it kind of makes sense to use that complexity measure. But what about high dimensions? Like, should we continue still using this default? So these complexities, that was a lot of criticism 3-4 years ago that VC theory is dead in higher dimensions because it just doesn't work. And the reason is, yeah, those were justified in low dimensions. So we need to revisit many notions of complexity measure. People have tried to explain why different kinds of measures. And our talk is like trying to, use MDL to derive one complexity measure and see what can we say with that from that lens. So that's what we'll try to do in this talk. So the principle is simple, that choose the model that gives the shortest description of data instead of simplest model. Now we have shortest description that comes into the principle. And as I think previous talk said, it is very closely connected to the Kolmogorov complexity, as it's often seen as a computable version of Kolmogorov's complexity using Shannon's information theory. And in simple language, I mean, I guess this audience is very familiar, but for ML audience, it's useful to do this mapping that models are seen as probability models. And in MDL world, you think of a model Q as a code which encodes some particular observation with certain number of bits. And here in ML, you want to have a good fit maps to the word shorter code length or shorter description. So this is like a test error. This might be like the test code length. And over the years, there have been many forms of MDL, like two-stage MDL, mixture MDL, normalized maximum likelihood. So I'll briefly recap the fundamental concepts and then try to apply them to high-dimensional model and see what comes out. So as I said, MDL wants to have an optimal coding. The question is, what do we mean by optimality? What are the notions of optimality used? So when you have a correctly specified generative model, there are like two possible or like two usual objectives. One is, because we have a correctly specified generative model P star, this is the code length log 1 over P star Y that encodes the number of bits. And then if you use any other code or like any other model, the number of bits is log 1 over QY. You take expectation over all possible Ys from P star and you try to minimize Q to find the optimal code. Or you can say, well, we'll do min-max version of it. So instead of expectation, I want to claim, like I want to choose a code that has the best worst case code redundancy, because we are comparing to the Oracle log 1 over P star code length. And you can see kind of like this is scale divergence plus entropy, that the optimal code in these both objectives actually turns out to be just P star. So that's when you have a true generative model. And one of the advantages of MDL is you don't really need a generative model to talk about optimal code. So in the second case, when you don't have a generative model, this log 1 over P star Y changes. And now you're given a set of codes and you're trying to find the best code with respect to that set of codes. So the best code for any observation would be just the best possible code length for that observation. And you're doing the min-max version because there's no P star to take expectation over. So this notion generalizes and you have replaced log 1 over P star to some Oracle min theta log 1 over P theta Y. So that's the objective that is typically used. And it turned out that Shatarkov in 1980s, he showed that there is an optimal code that doesn't lie in this parametric family. Suppose this was a parametric family, and it's called the NML code, normalized maximum likelihood. That is given by, for observation y, you max theta p theta y and divide by this normalization. Then that code is the optimal code if you want to do this worst case, find a worst case, a best possible code from a worst case perspective without using a generative model. So that's a brief tutorial on how MDL tries to find an optimal code. And then the question is, what is the complexity from this perspective? So the typical complexity measure, log of this is used often. So this normalization constant here, that is used as the complexity measure. No. So this log of that is seen as the complexity measure, and you can show that that's actually the worst case redundancy. That's easy to show. It's also the expected redundancy if you put a generative model. And it was shown that when you have d-dimensional parametric codes, then in the underparameterized regime, this again simplifies to d over 2 log n. So you recover again the parameter count as the complexity measure. But there are challenges with this complexity, and this is what the rest of the talk tries to deal with and find some solutions. Whether you like the solution or not is up for debate, but we'll propose something. So when this is infinity, then the code is not defined because the denominator is infinity, and the complexity is also not defined. So the prior work, so even like simple models like linear models, you can show that if you have like a reasonable class of theta, so you're doing OLS in some, so this is like an OLS, you plug in the OLS, then this whole expression integrates to infinity. The easiest way to think about this is in high dimensions or overparameterized regime, you interpolate, so this is 0. So you're integrating exponential of 0 over real numbers, which will be infinity. So that's called the infinity problem. And it becomes a bottleneck, especially for us, if you're trying to deal with overparameterization. So in the past, like even in low dimensions, you have this infinity problem. So people have tried to argue, well, let's truncate the output space. But more recently, and in this talk, people started revisiting it from a regularization perspective. Can we regularize and try to understand if the complexity helps us, gain some useful insights? So we'll be using ridge regularization and building a complexity measure, and then trying to argue like what insights it gives us and how we can use it. Like, is there something useful that we can say about double descent, and or can we use it in practice to do something that is possibly useful? And we use ridge regularization for a reason. Well, two reasons, to be honest. One is, as I showed, you often see U-shaped curves with ridge regularization, and you always see a better performance than the typical estimators. And the other thing is, ridge regularization does enable us to do, analytic calculations so that you can say something more than just here is an expression evaluated. We can actually compute it and talk about what it scales like in different settings. So that's the setup so far that we're trying to understand from MDL perspective. There is a complexity measures which don't work easily in high dimensions or like overparameterized regime. And we are going to try to fix it in some way and argue how that is useful. So the way to think about this regularized or normalized maximum likelihood is it's called luckiness normalized maximum likelihood. And the way it works is, instead of doing just max over p theta y, you do a weighting with respect to theta. So it's some sort of prior you put on your theta space, and then you try to maximize this to define your codes. That W theta is called luckiness function. And our approach is that, well, how do you choose this W theta? So as I said, we'll do ridge regularization. So we have W theta that will depend on the regularization parameter lambda. And if you plug this in here, now you can see instead of OLS, if this was a regularization term, this will become regularized OLS. And then you plug that in. So you have theta hat lambda, and you have this kind of expression. So now your code length is proportional to e to the minus the likelihood, max likelihood time plus some regularization time. So that's a very simple modification. And question is, so how do we define complexity using this modified set of codes? And the way we define it is like, we now have a family of codes, so we'll try to find the best possible code in this family. So that's how we'll define the complexity. So now we have log 1 over q lambda y. And again, to do analytical derivations, we put a baseline, which was like, we assume a generative model, but in experiments, you can ignore this term and you still have some meaningful results. So this would be our baseline. And you can see that this, I mean, it's just an offset. It doesn't really affect the optimization, but this expectation does affect the optimization of this expression to get the complexity measure. And then you have to choose what kind of regularization parameters will you allow. So we allow for a rich class of lambdas that are simultaneously orthogonally diagonalizable with the X matrix in linear models. And now, so these are like a bunch of things you have to deal with because you're changing the complexity measure. Is now, because you have regularization, you have to account for the code length of this regularization. And we do a two-stage MDL version of it. So it's like, you know, a discretized code length for each coordinate. And then we define the MDL complexity as, you know, the best possible redundancy and the code length that you would need to encode the optimal regularization. So those are the two terms. And we divide by n because, you know, n has the number of samples. So this is the excess code length that you need compared to this oracle to transmit your data from an MDL perspective. And that's why we call it the MDL complexity. So the main result that I'll talk today, and the paper has other cases too, is the simple linear model case in higher dimensions, because as I said, we're trying to do analytical derivations. And so if y is coming from x theta star comma sigma square, like normal, so basically mean is x theta star and noise variance is sigma square, and x transpose x diagonalizes as u times some eigenvalues times u transpose, and w denotes your signal in the rotated eigenbasis. Then the minimum minimum excess code length without the regularization is as follows. So it's just 1 over n log 1 plus rho I wi square by sigma square. So rho I is the eigenvalue, wi by square by sigma square is like the signal in that direction. So that's what the code length looks like. And then when you add in the code length, because you are using regularization, so you have to encode, then it becomes rho I plus sigma square by wi square plus some constants that you like, depends whether you want to track them or not up to a certain resolution. So moral of the story on this slide is that this reformulation allows us to derive analytical expressions that are not just parameter count, because they do have dependence on the design, they have dependence on the signal strength and the noise variance. So you can try to understand better like the decomposition of your complexity other than crudely just bounding this by d over n.
Yeah. The luckiness function, I remember when you introduced it a lot. What is it actually doing? Its intuition for this luckiness function.
Sorry, 1 second. So this is what it's doing is basically saying that I favor some thetas more than the other theta. So it's like putting a prior on your parameter space so that the complexity remains finite. Okay. So you're just putting in prior information in the form of theta.
Oh, okay. Just any prior information.
Yeah. So, and what we do is like, well, which prior should you choose? And that's why we're like, for each prior, you have a different code, different NML code. So now how do I think about complexity? Because you'll get a different answer for each lambda. So the way, because complexity to us is the max, the best possible you can do. So the way we define complexity is best possible code that can be derived from this format. Thank you. Yeah, I understand this thing gets slightly, it gets tricky. And in paper, we argue why, like, all these choices are kind of necessary, because if you try to deviate a little bit, you don't resolve the infinity problem. So you remain like, MDL doesn't inform very well what to do. So, well, these expressions, can we unpack it? So it's simple to visualize it. We write expressions in the paper. So this is what it typically looks like. For a lot of designs, probably one of the most interesting design, like the simplest design is take your covariates to be Gaussian, fix the sample size. So this is a fixed data set. And what I'm varying on the x-axis is the fitted model. Okay. So this is consistent with how we should visualize bias variance trade-off curves. And y-axis, we are plotting the MDL complexity. X-axis is the parameter count, the conventional complexity. These are 4 different settings. So you can think of settings as what is the true dimension, that's D star. And alpha is like the decay of your eigenvalues of your covariates. So it's, as I said, it's a function of all these parameters. So we have 4 curves, but they qualitatively look similar. What does it say? It says that, well, complexity that we have derived scales like D over N till D by N is equal to 1. So it has the canonical, parameter count kind of scaling. But beyond that, it grows slowly. It grows like logarithmically in D. So in some sense, we are saying that the complexity grows linearly, and then it slows down. Your space is not growing too fast. So that was kind of surprising to us in some sense. Maybe it's not surprising in hindsight, because it depends on the eigenvalues of X, and you don't have too many, like when D is greater than N, the number of eigenvalues are not growing. It remains stuck at N. Only the eigenvalues grow slowly. So, but that was the surprising bit to us, is that we do have parameter count here, but no longer in an overparameterized regime. And in the interest of time, I wouldn't talk about, like, there are some other optimality properties about MDL, that it minimizes the in-sample risk, like it is related to minimizing the in-sample risk. It also represents, like our code extracts the best worst case redundancy. I talked about 2 possible notions. So it does have that kind of optimality properties. And then we are only talking about in this talk about linear models, but you can extend it because, it's ridge regularization. You can extend things to kernel ridge regularization. So it's you can extend it to kernel methods. And in those settings, it again informs some sort of classical in-sample risk bounds. So those are some other optimality properties of our MDL comp formulation, trying to justify that it's not too ad hoc, although there were a few judgment calls that had to be done to define it to solve the infinity problem. But let's come back to the original motivation. Like, what can we say about double descent? Like that was the goal. The kind of a surprising bit, but maybe not a disappointing bit, is that MDL still remains monotone. Like it is like D over N log D. So the complexity is not like it's what we thought originally would be, that after D, maybe the complexity starts to reduce. It doesn't. It grows, it just grows slowly. So it means that if I change the x-axis from parameter count to MDL comp, I'll still see all those curves. I would not change the shape of the curves. So then, but maybe that's not an issue, because that hints that more likely it is that double descent is a property of the estimator rather than the problem itself. And that is kind of consistent with other now growing wisdom, that the estimators often become unstable around D is equal to N if you don't regularize them strongly, because the implicit regularization that people have started talking about kind of breaks down in that regime. So in some sense, slightly disappointing bit, but hindsight, it makes sense. And as I said, this conclusion is not contradictory, because other papers have tried to characterize when these estimators will work well. So they found sufficient conditions for these estimators to work well, but they don't always work well, is also well known. So that's the summary for double descent. And I can show, so we have these complexity notions. Now, can we use it for something that would be more interesting from practice viewpoint rather than just deriving expressions? And one natural point would be to derive generalization bounds, which tried for a bit, couldn't. So then we tried to flip and like try to use it in a more in a simpler manner. And what we end up realizing that you can actually use this MDL perspective to do hyperparameter selection. So what you do in ridge regression is you have this, like you can just derive from our theorems, and later on we realize that other people have suggested some version of this, that you, to tune a lambda say in ridge regression, you just write down the objective, the regularization, and add this complexity term that comes from our paper, like from our results. And then you choose lambda just based on minimizing this. So, and the row i's here are the eigenvalues of your X transpose X matrix. In kernel regression, it would be, everything would be the same. X will become K. This will become the norm of the alpha, and this would be the eigenvalues of the kernel matrix. In simulations, one can try to ask, like, how does this objective correlate with the test MSE? So this is what I'm trying to plot here, because as you vary lambda, your test MSE would change and your practical MDL comp will change. And from here, you see that, well, the objective remains kind of flat, but the two test MSE and objectives are both kind of minimized in the same region, saying that this might be a good proxy. And because remember, test MSE is something we don't know. Suppose we are in a limited data regime, so we don't have validation data, or like we don't know the true test MSE. But this is just based on training data. So you can plot this and you see a cross range of D over N settings. So this is like the overparameterized regime. You see that practical MDL comp objective does try to, it correlates with where test MSE is small. So suggest that this might work well to tune lambda. And well, it does remove the double descent if you tune lambda by this, because as I said, ridge regularization does remove all this peak business because estimators are stable. So I'll show some experiments quickly and end. Basically that you can use this objective instead of cross-validation. And compared to cross-validation, like we only have one-fold computation. So if you're doing k-fold cross-validation, our objective is k times better computationally. We tried on a bunch of PMLB data sets. In the interest of time, I would not describe the details. That this is the plot that tries to argue that our method is competitive to cross-validation. So this is a different setting. So D over N is equal to one mean that the number of features is same as dimensions. Here you see that the MSE that you get from cross-validation is slightly higher than you get from MDL comp. And as you increase D over N, it like this method is better than the other method. And when you are in the low parameterized regime, under parameterized regime, then like either one is okay. So point is, from this slide, what I'm trying to say is our method provides a competitive alternative to cross-validation while saving computational resources. And then we also tried it on some fMRI data set and compared it with some other baselines that tried to induce sparsity. And we found that in this data set, we beat some Bayesian ARD regression tuning quite a bit, slightly worse than the cross-validation, but not too bad. Okay, so let me just end with this slide that we try to revisit complexity measure to understand what's going on in overparameterized regimes for double descent. We recover some complexity measure, which is not just parameter count. And interestingly, it doesn't have the D over N scaling in overparameterized regimes. It hints that the double descent is likely to be the choice of estimator, which is now, I think, kind of sort of consensus in the literature, but maybe depends on which literature I'm talking about. And then it gives us a good competitive to cross-validation, but computationally better tuning procedure. The open questions are like, how do we derive a good out-of-sample generalization? We have in-sample generalization bounds and going beyond regression. So that's it. Questions? Oh, yes.
It's more a comment. Do you know about sequential MDL?
I do.
Yes, yeah. I mean, that is a very neat way of, even huge, large language models, more parameters than data, right? To honestly get a code length out of it. And that is also a very different way of getting proper code lengths and comparing models. So have you thought about this or compared it? Or?
That's a good point. So while we were writing the paper, there was some works that were trying to use frequential version of it.
Yes.
And they said it's like empirically it seemed to inform, but like there were no like analytical derivations. But are you suggesting that one can do analysis easily too, even with complex settings?
I don't know. It may be hard, but I know that empirical they work excellent. I mean, they're actually top performers on my compression contest now.
Oh, okay.
So they take huge transformers and and honestly compress this gives a self-extracting archive. So the point is that you don't have to transmit or store the neural network with trained weight, but so that the initial number is very small, right?
Yeah.
And
so
they're just too slow.
What is too slow?
They're too slow to qualify, sort of. They're much slower than conventional compressors.
Oh, I see. I see too. But yes,
otherwise, I mean, you just specify. I mean, you specify the learning algorithm, you specify the architecture. Essentially, the initialization of the neural network you have to specify.
Yes.
Because on the decompressor side, you run the training
in
the same way as the compressor side.
Yeah.
And that works in practice amazingly well.
Oh, I will be happy to check it out. Yeah.
Yes. Yeah.
Thank you. Yeah. Okay. Yes. Yeah. You're sorry. Yes.
So again, it's kind of a comment kind of question. So with like from a overall complexity perspective, you have thought that looking at the number of parameters is perhaps missing. So like the complexity of a number itself, one number can vary quite a lot. So the complexity of number 2, or the complexity of number 2.7115321 is quite different.
Yes.
So I don't know, has that ever been pointed out in any of these kinds of discussions that the actual, it's not just the number of values, but the values themselves could be more or less complex.
Yeah. So I think there has been like there has been work on people trying to argue that you should look at other kinds of norms, the size of the weight rather than the count of the weights, but not exactly what you say. Like people have tried to argue that you don't need to store the numbers to very high precision. And like you can, sketch it noisy, like instead of 64 bits, you can use 32 bits, that kind of. But I think the motivation for us was more like trying to push back on this default use of parameter count and saying, oh, neural networks do great despite so many parameters. But other than what qualitatively I said, I haven't seen much of what you're suggesting.
So, I mean, so this B half log n, and that comes from a crude approximation from the true underlying sort of MDL principle, or maybe the MML principle is actually more sort of fundamental. Right. And you can derive correction terms, which is then called refined MDL, and sort of if you wiggle a parameter right, it may have more or less influence on the output, right? And you can quantify that, and the next order correction is actually sort of the Fisher information, which quantifies the sensitivity of your probability to the parameter. And then you get this extra term, so you have the B half log n. So the linear term in n is the log probability that scales linear with n. Then you have B half log m, which is sort of the first term in MDL. And the second term, the constant term, you can specify, which is the square root of the determinant of the Fisher information matrix. And then comes, terms which vanish with n, which is sort of a significant improvement. The two problems are, it is impossible sort of to really compute for, very large models, right? And the second is that even this will work terribly for heavily overparameterized models, because then and that's what I think, the small O of 1 terms, which actually tend to 0, are still dominant.
I guess it was, but yeah, I understand. Thank you.